August 15, 1940. High above Kent, a British Hawker Hurricane dives after a fleeing Messerschmitt Bf 109. For months, German pilots had relied on one simple escape tactic. Push the aircraft nose down into a steep -G dive, and the British fighter behind them would hesitate or lose engine power completely. The reason was hidden inside the Rolls-Royce Merlin. Its float carburetor depended on gravity to regulate fuel flow. During sudden -G maneuvers, fuel surged upward, the float valve closed, and the engine starved. Pilots described the result vividly. The Merlin coughed, sputtered, then sometimes died entirely for several terrifying seconds. In aerial combat, several seconds could mean death. The Germans did not suffer from this problem. Their Daimler-Benz DB601 used direct fuel injection, allowing the engine to keep running perfectly during violent dives. Luftwaffe pilots exploited that advantage constantly during the Battle of Britain. Push down, escape, survive. British pilots hated it because they knew exactly what was happening and had almost no way to stop it. The long-term engineering solutions already existed in theory. Pressure carburetors, fuel injection systems, complete redesigns. But Britain did not have time for that in 1940. The RAF needed something immediate, something simple, something that could be installed quickly across operational squadrons. That solution arrived through Beatrice Shilling at the Royal Aircraft Establishment in Farnborough. Shilling was one of the most skilled engineers working in Britain during the war. She held a master's degree in engineering and was also an accomplished motorcycle racer with a gold star from Brooklands for averaging over 100 miles per hour. She understood machinery intuitively, and she understood exactly where the Merlin was failing. The genius of her solution was its simplicity. Instead of redesigning the entire carburetor, Shilling created a tiny metal restrictor disc with a carefully calibrated hole drilled through its center. The disc limited fuel surge during -G maneuvers, just enough to keep the engine running. It weighed almost nothing, cost almost nothing, and ground crews could install it rapidly using ordinary tools. The modification became famous throughout fighter command under an unofficial nickname, Miss Shilling's Orifice. Pilots loved it because it worked. British fighters suddenly began following German aircraft into dives far more aggressively. The old Luftwaffe escape maneuver stopped functioning reliably. And in the skies over Britain, that changed everything. The first German pilots who encountered the modified RAF fighters probably did not understand immediately what had changed. From their perspective, the laws of combat themselves suddenly seemed unreliable. For months, the -G dive had functioned almost perfectly as an escape maneuver. A Luftwaffe pilot could push the nose sharply downward and expect the British fighter behind him to lose engine power before maintaining pursuit. The maneuver had become instinctive, automatic, a trusted part of German fighter tactics during the Battle of Britain. Then suddenly RAF fighters started staying with them through the dive, still accelerating, still firing, still dangerous. The change shocked German pilots because aerial combat depends heavily on expectation. Pilots survive by building habits and trusting them under extreme pressure. If a maneuver works repeatedly enough times, it stops feeling like a risk and starts feeling like certainty. The -G escape had become certainty. Then the certainty disappeared. A German pilot would push nose down expecting the familiar silence behind him only to glance backward and still see a Supermarine Spitfire or Hawker Hurricane holding position through the dive. Engine roaring, closing distance, still fully in the fight. That realization changed the psychological balance of combat immediately. The restrictor itself was not a perfect solution. That is important to understand clearly. The German Daimler-Benz DB601 remained technically superior because true fuel injection handled -G conditions far better than the modified Merlin carburetor ever could. Under severe maneuvers, the British engine could still stumble occasionally. The restrictor did not magically transform the Merlin into a fuel-injected system. But perfection was never the goal. The British only needed to remove the worst part of the disadvantage. And that is exactly what Shilling's restrictor accomplished. Before the modification, RAF pilots often entered dives already expecting engine trouble. They knew what would probably happen. The cough, the sputter, the terrifying few seconds of silence while the propeller windmilled uselessly. That hesitation changed the way they fought. After the restrictor, many pilots described feeling dramatically more confident during combat. They trusted the engine more and pursued German fighters far more aggressively. That psychological shift mattered enormously. A pilot who trusts his aircraft becomes more dangerous, more decisive, more willing to commit fully to violent maneuvers. Combat aviation depends heavily on confidence, and the restrictor quietly restored some of that confidence to fighter command. The Americans faced remarkably similar problems in aircraft powered by the Allison V-1710. Early American fighters like the Curtiss P-40 Warhawk and Lockheed P-38 Lightning also relied on carburetor systems vulnerable to -G fuel starvation. American engineers generally favored more ambitious long-term solutions involving pressurized fuel systems and redesigned carburetors. Those systems eventually worked well, but they required time. And Britain in 1940 did not have time. That was the true genius of the restrictor. It could be installed immediately across operational aircraft while the Battle of Britain was still raging overhead. Other nations inherited engineering strengths or weaknesses almost accidentally through engine choice. Italian fighters using German Daimler-Benz engines automatically inherited fuel injection advantages. Meanwhile, aircraft like the Japanese Mitsubishi A6M0 later suffered from -G vulnerabilities very similar to those of the early Merlin. American pilots in the Pacific eventually learned to exploit those weaknesses exactly the way German pilots once exploited British fighters over England. In war, tiny engineering details become tactics, and tactics become survival. The Battle of Britain itself was fought on terrifyingly narrow margins. Radar mattered. Pilot training mattered. Aircraft production mattered. Ground crews mattered. Leadership mattered. No single washer with a hole in it decided the campaign alone. But wars are often shaped by accumulation rather than spectacle. Every escaped German pilot returned to fight again tomorrow. Every successful RAF pursuit mattered. Every British pilot surviving one more engagement mattered. The restrictor did not win the battle by itself, but it unquestionably made an already difficult fight less difficult. And during the summer of 1940, even small advantages mattered enormously. Later Merlin engines eventually received pressure carburetors and improved fuel systems that solved the problem much more completely. By 1943, the issue had largely disappeared from frontline British fighters. But those solutions arrived later in the war. Shilling's restrictor bridged the dangerous gap between immediate survival and long-term engineering progress. That bridge may have saved countless lives. Today, surviving examples of the original restrictor discs remain preserved in places like the Royal Air Force Museum, London. Most visitors barely notice them. They look ordinary. Tiny metal washers with drilled holes. Nothing visually dramatic or impressive at all. And yet those simple pieces of metal quietly changed fighter combat during one of the most important air battles in history. The Messerschmitt Bf 109 continues diving toward the Earth. But now the German pilot realizes something has gone terribly wrong. The British Hawker Hurricane behind him is still there, still accelerating, still holding position through the dive. Its engine is still running perfectly. For one brief moment, the entire logic of the engagement reverses. The maneuver that had protected Luftwaffe pilots throughout the Battle of Britain suddenly stops working the way it always had before. And now the danger belongs to the wrong man. For months, German pilots had trusted the -G dive almost instinctively. The tactic had proven itself repeatedly in combat over France, the Channel, and southern England. Push the aircraft nose down sharply. Force the British pilot to follow. Wait for the Merlin engine to cough and die. Escape while the RAF fighter hesitates helplessly behind you. Simple, reliable, deadly. The tactic became part of Luftwaffe muscle memory because experience kept confirming it. Then suddenly British fighters began staying with them through the dive. Still dangerous, still firing, still closing the distance. That change mattered psychologically as much as mechanically, because combat pilots survive by trusting patterns. And once trusted patterns begin failing unexpectedly, uncertainty enters every engagement afterward. The German pilot in the dive does not know anything about fuel restrictors or carburetor modifications. He does not know about the engineers working at Royal Aircraft Establishment in Farnborough. He does not know about a woman named Beatrice Shilling carefully studying fuel flow behavior inside Merlin engines. All he knows is that the British fighter behind him should not still be there. But it is. And in aerial combat, Confusion lasting even a few seconds can become fatal. That was the remarkable thing about Shilling's solution. Its effects appeared directly inside combat before most people fully understood the engineering behind it. The modification itself was astonishingly small. A simple metal restrictor disc. A carefully drilled hole calibrated to limit fuel surge during sudden negative G maneuvers. Nothing visually dramatic. Nothing complicated enough to resemble some revolutionary wartime invention. And yet that tiny piece of metal quietly changed the behavior of RAF fighters across Britain. The brilliance of the restrictor lay in precision, not complexity. Many engineering failures persist because people attack symptoms instead of causes. Shilling understood exactly where the Merlin was failing and focused only on that point. The carburetor itself did not need complete redesign immediately. The engine did not need replacement. The aircraft did not need rebuilding. The problem was fuel surging violently upward during negative G conditions and temporarily starving the engine. Control the surge, and the fighter survives the dive. That clarity of understanding made the solution possible. The British situation in 1940 also demanded exactly this kind of practical engineering. Britain did not possess unlimited time or industrial freedom during the Battle of Britain. Fighter command was already under enormous pressure. Aircraft losses mounted constantly, while factories struggled to replace damaged machines quickly enough. Pilots flew repeated sorties with little rest. Ground crews worked exhausting hours repairing, refueling, and rearming fighters between engagements. There was no possibility of grounding entire squadrons for complicated redesign programs. The war was happening now. Every solution had to function operationally and immediately. And that is exactly why the restrictor became so valuable. Ground crews could install the modification rapidly using ordinary tools. No major engine removal. No factory reconstruction. No weeks of testing before operational use. A mechanic could fit the restrictor directly into frontline aircraft while the battle itself continued overhead. That practicality mattered enormously. A perfect engineering solution arriving too late solves nothing in wartime. Shilling's restrictor bought Britain time. And time may have been the single most valuable resource Britain possessed during 1940. Pilots noticed the difference quickly. Before the modification, many RAF pilots entered steep dives already expecting engine trouble. The negative G weakness had become familiar and deeply frustrating. Pilots described the same sequence repeatedly. The Merlin coughing, fuel starvation, temporary silence. A terrifying moment of helplessness while the German fighter escaped below them. That helplessness mattered psychologically because fighter pilots depend heavily on trust in their aircraft. A pilot uncertain about his engine fights cautiously. A pilot confident in his machine fights aggressively. After the restrictor appeared, that confidence began returning. RAF pilots increasingly followed German aircraft into dives without the same hesitation. Pursuit tactics became more aggressive because the pilots trusted the Merlin to keep running long enough to remain effective. That change altered combat behavior throughout fighter command. The aircraft themselves had not suddenly become radically different machines, but the pilots flying them had changed. And sometimes that matters just as much. The German Daimler-Benz DB601 still remained technically superior in several respects. Its fuel injection system represented excellent engineering, and Luftwaffe pilots used that advantage intelligently and effectively. The British restrictor did not erase German strengths entirely. It simply removed enough of the imbalance to restore tactical flexibility to RAF fighters. And in warfare, removing a weakness can matter every bit as much as creating superiority. Other nations experienced similar engineering strengths and weaknesses depending on engine design. Italian fighters powered by German Daimler-Benz engines inherited fuel injection advantages automatically. Meanwhile, aircraft like the Japanese Mitsubishi A6M0 later suffered from negative G vulnerabilities very similar to those affecting the early Merlin. American pilots in the Pacific eventually learned to exploit those weaknesses exactly the way German pilots once exploited British fighters over England. The logic repeated itself across different wars and different skies. Tiny engineering details became tactics, and tactics became survival. The Battle of Britain itself balanced on extraordinarily narrow margins. Radar mattered. Aircraft production mattered. Ground crews mattered. Leadership mattered. Pilot skill mattered enormously. No single washer with a drilled hole won the battle by itself. History is never that simple. But wars are often shaped by accumulation rather than spectacle. Every German fighter that escaped successfully returned tomorrow. Every RAF pilot surviving another engagement mattered. Every small engineering improvement rippled outward invisibly across hundreds of encounters. The restrictor quietly influenced countless moments that never appeared in official reports or newspaper headlines. Later Merlin variants eventually received pressure carburetors and improved fuel systems that solved the negative G problem much more completely. By 1943, the issue had largely disappeared from frontline British fighters. But those solutions required years of development and production. Shilling's restrictor bridged the dangerous gap between immediate necessity and long-term engineering progress. Without that bridge, RAF pilots would have continued entering combat with a severe tactical weakness for far longer. Today, surviving examples of the original restrictor discs remain preserved quietly in places like the Royal Air Force Museum, London. Most visitors barely notice them. And honestly, that reaction makes sense. The devices look completely ordinary. Small, dull metal washers with carefully drilled holes. No moving parts. No dramatic complexity. Nothing about them visually suggests strategic importance. They resemble forgotten hardware from the bottom of a toolbox. And yet those tiny pieces of metal helped reshape fighter combat during one of the most important air battles in history. That may be the most extraordinary part of the entire story. Wars are usually remembered through giant machines, famous speeches, and enormous battles. But history also turns quietly on invisible details. A valve, a fuel line, a tiny restrictor hidden inside an engine. One engineer understanding exactly where the failure existed and solving only the part that mattered most. Beatrice Shilling never commanded armies, never became a famous wartime celebrity, never flew combat patrols over Britain. But during the Battle of Britain, she helped remove a deadly weakness from RAF fighters using nothing more than engineering precision, practical intelligence, and a remarkably simple idea. A woman with a master's degree in engineering. A motorcycle racer capable of averaging over 100 miles per hour at Brooklands. And an exceptionally clear understanding of where fuel goes when gravity stops cooperating. Return one final time to that sky above Kent. The Hurricane dives hard after the retreating Messerschmitt. The German pilot still expects the familiar silence behind him. Instead, he hears the impossible sound of the British engine still roaring closer through the dive. The old rules are gone. The escape no longer works. And suddenly the sky belongs to the wrong man.